Hi, today we're learning about the distributive property and factoring out the greatest common factor. First, let's recall the idea of area, which is just how much of a flat surface a shape covers. So this rectangle, since it covers 6 little squares, has an area of 6. This one has an area of 9. And this one has an area of 12. It covers up 12 little squares. Take a look at the orange rectangle. What is its area? The area of the orange rectangle is 12. You could count that it covers up 12 little squares. Also, you might have noticed that it was 6 squares tall and 2 squares wide. And to know the area of a rectangle, you can multiply those two dimensions. What if you knew the area of a rectangle was 15? What could be the lengths of its sides? The only correct answer is 3 by 5. A 3 by 5 rectangle would cover up 15 squares. Since its two dimensions were 3 and 5, and 3 times 5 is 15. None of the other choices work. For example, a 10 by 5 rectangle would cover up 50 squares. Whether you realized it or not, what you just did by answering this question was to factor the number 15. When you factor anything, it just means you break that thing into parts that multiply to make that thing. So if you were asked to factor the number 30, which choice would be correct? In choice C, we've broken up the number 30 into 3 things that multiply to make 30. 5 times 3 times 2 is 30. None of the other choices fit the definition of factor. Let's take a look at the area of a few very specific kind of rectangles. A 1 by 1 rectangle would just have an area of 1. It covers up 1 square. This rectangle has an area of 3. It's 1 by 3. This 1 by 4 rectangle has an area of 4. Take a look at this purple rectangle. What is its area? Like the others, it's 1 little square tall, but the length is somewhere between 5 and 6, and we can't really tell how long it is. Luckily, algebra gives us ways to work with numbers when we're not really sure what they are. So take a look at the picture of the purple rectangles. How do you think we could represent its overall area? That picture would represent 3x, which is the way that we write 3 times x. You might have noticed that its length was that unknown length we were calling x, and its other dimension was 3. It's 3 spaces tall. So we can think of this quantity as the area of that rectangle, 3 times x. But we also might have noticed of these pieces that we were calling x, there are 3 of them. So in this picture, there's 1 negative unit, and there are 2 of the x units. So what if I take 4 of them, so that its length is still 2x minus 1. 2x is in a negative 1. But now its other dimension is 4. It's 4 spaces tall. Which of these expressions is equivalent to the 2x minus 1 times the 4? The equivalent expression is choice A, 8x minus 4. We notice that altogether we have 8 of the x pieces, and we also have 4 of the negative 1 units, 8 x's and a negative 4. Algebraically, we can think of this as multiplying both of those terms, the 2x and the negative 1, by 4. 4 times 2x would be 8x. 4 times the negative 1 would be negative 4. So altogether, we have 8 x's and 4 negative units. So which expression is equivalent to negative 3 times 4 minus 5x? The equivalent expression is choice D, negative 12 plus 15x, which algebraically we can get by multiplying the 4 by the negative 3 and also multiplying the negative 5x by the negative 3. We're just going to make this area idea a little bit more complicated. If we take this x distance, the somewhere between 5 and 6, we don't really know how long it is, x distance, and multiply that by another x. So now I've got a square that is x wide and x tall. How do you think we could write the area of this shape? We've already talked about how we can think of the area as the product of the dimensions, and x times x, another way to write that is x to the second power, or x squared. In fact, that's why the second power is called squared, because if you have a shape that's the same length in each dimension, you have a square. So let's say we start with 2 units and 3 of the x units. They're negative, so they're red, but still there's 3 of them. And we multiply this quantity by the length x. How much do we have altogether? What's the area of this whole thing? Altogether, we have 2 of the x pieces, those green ones on the side, and we have 3 of the negative x squared pieces. Algebraically, we could individually multiply the 2 by the x and the negative 3x by the x, coming up with 2x is our first term, negative 3x squared is our second term. So remember, the idea of factoring is just going the other way, starting with something and figuring out what you could multiply together to get it. So if we start with 2 of the x pieces and 3 of the negative x squared pieces, and we want to factor that quantity, we're just reversing the process. Geometrically, we could think of it as taking these pieces all together and fitting them into a nice rectangle with well-defined dimensions. Algebraically, we can look at each term and see what they have in common. 2x is the same thing as 2 times x. 3x squared is the same thing as 3 times x times x. And what they have in common is 1x. So if we're looking for things that multiply together to make 2x minus 3x squared, we can kind of undistribute the x. So x times what would get us the thing we started with? Well, we look at what's left over. A 2 in the first term and a 3 and an x in the second term. So now you're going to try step by step. We're going to factor 6y to the third power minus 9y to the second power. We'll look at what each of these terms means. 6y to the third is the same as 2 times 3 times y times y times y. 9y squared is the same thing as 3 times 3 times y times y. What's the biggest factor that appears in both the blue and the red box? That would be 3y squared. There's a 3 in both of the boxes, and there's a y times y in both of the boxes. We call 3y squared the greatest common factor. It's the biggest thing that's a factor of both terms. It's the biggest thing that divides out of both terms. So if we're looking to factor 6y to the third minus 9y squared, we can undistribute that greatest common factor. Take a look at what's left over in both of the terms, which is the expression written in factored form. That would be choice A. In our first term, we have a 2y left over, and in our second term, there's a 3 left over. Try this one all by yourself. Factor 8nz to the fifth minus 6n squared z to the third. The equivalent expression is choice B. First, we look for what these two terms have in common. 8nz to the fifth would be this all factored out. 6n squared z to the third would be this all factored out. What they have in common is a 2, an n, and 3 z's. So that's our greatest common factor. And then what's left over is 4z squared in the first term and a 3n in the second term. So there's our other factor. We've been learning about the distributive property and factoring out the greatest common factor.